This is Steve Fowkes welcoming you back. This segment of the presentation begins with NADH and the antioxidant defense system. NADH is the underlying foundation of the antioxidant defense system. NADH carries reducing power. In other words, it's cold. When NADH transfers its reducing power, where cycle 1 touches cycle 2, it becomes NAD, which is the oxidized form ready for collecting more energy. And the NADP becomes reduced to NADPH, which is the initial reservoir for reducing equivalents. But it doesn't stop there. Where cycle 2 touches cycle 3, glutathione reductase uses NADPH to reduce oxidized glutathione, GSSG, back into reduced glutathione, GSH. The pool of reduced glutathione is the single largest reservoir of reducing equivalents in the body. It is the chemical foundation of life and the key to a non-Alzheimer brain. Other antioxidants, like vitamin C and vitamin E, rely upon glutathione for their recycling. Glutathione is the primary cellular antioxidant because it contains an SH group. The SH group is its active site for both its antioxidant activity and its mercury binding activity. Mercury has an extreme preference for binding to sulfur, as evidenced by the primary mercury ore in the Earth's crust, cinnabar, being mercury sulfide. Because of the special affinity of mercury and sulfur, all sulfhydryl-containing enzymes are at risk for mercury poisoning. Mercury is not the only element with an affinity for sulfur. Lead also preferentially binds to sulfur, and lead sulfide, galena, is the primary lead ore. Although lead toxicity does not seem to be sufficient for inhibiting the sulfhydryl enzymes that trigger Alzheimer's disease, lead toxicity may be involved in increasing Alzheimer's risks indirectly, possibly through aggravation of insulin resistance or increasing sensitivity to inflammation. So it's probably a good idea to assess all toxic metals as part of an Alzheimer's prevention reversal program, including iron. Now that mercury toxicity is identified as the domino-tipping influence in the Alzheimer's disease cascade, let's switch our attention downstream by following the dashed magenta line. We have already covered some of the ATP impairments with the discussion of creatine kinase and its 95% inhibition in Alzheimer's disease. Creatine kinase is an example of a sulfhydryl enzyme that is common to the body and brain. But let's shift our attention to the other sulfhydryl enzymes that play an even more dominant role in the brain. No example is more apt than the kinase and phosphatase enzymes that regulate the brain's phosphorylation cycle. Kinases and phosphatases are classes of enzymes, some of which have sulfhydryl groups at their active sites. Kinases add phosphate groups to other molecules, like creatine kinase adds a phosphate group to creatine. Kinases also add phosphate groups to other kinases and to phosphatases, which changes their activities. So kinases are part of the regulatory feedback loops that adjust enzyme activity to meet metabolic needs. Protein kinase C is just one of the sulfhydryl-based kinases that is inhibited by mercury and in Alzheimer's disease. Protein kinase C is most highly expressed in brain tissue. Phosphatases work oppositely to kinases. They remove phosphate groups from enzymes and, like kinases, remove phosphate groups from other phosphatases and kinases, which can undo the activity alterations accomplished by the kinases. Because kinases can upregulate and downregulate the activities of other kinases, and up and downregulate the activities of their phosphatase counterparts, the kinase-phosphatase dynamic is not linear or stable. In fact, the system is wired to operate in a metastable state which tips into an overphosphorylated state before the phosphatases become active enough to reverse the process. The phosphatases then overdrive the system into an underphosphorylated state, which eventually turns off the phosphatases and reactivates the kinases. Brain enzymes and brain structures that are phosphorylated or dephosphorylated by these enzymes oscillate back and forth between being over and underphosphorylated every 90 seconds. This is one of the reasons why the brain, which is only 3% of the body's mass, consumes roughly 20% of the body's energy. This oscillation of phosphorylation probably has a fundamental role in maintaining the long-term stability of the brain. Although it may seem counterintuitive, oscillating systems tend to have superior long-term stability over damped systems. The ability of the female menstrual cycle to postpone a wide range of aging effects is but one example. This principle is also widely exploited in electronics to create circuits with extreme long-term stability. In the brain, one of the things that this oscillation accomplishes is cyclic adjustments of the cytoskeleton. With selective inhibition of protein kinase C and other sulfhydrokinases and phosphatases by mercury, the kinase-phosphatase dynamic is disrupted, which has catastrophic effects on the phosphorylation of brain proteins that are essential to the cytoskeleton. Like kinases and phosphatases, the cytoskeleton plays a much more dominant role in the brain than the body. Nowhere is this more true than with microtubules, the component of the cytoskeleton that provides transportation infrastructure for active transport of materials, which is indispensable for neural transportation down the exceedingly long axons and dendrites of brain cells. Microtubules are assembled and maintained with GTP as the energy molecule, and are depolarized and disassembled by the toxic effects of mercury. Please advance to Part 7 at this time.